Hello and welcome to Algebra 2 with Mr. Clausen. Today we're going to talk about graphing techniques for solving polynomials and identifying multiplicities. Specifically, what I want to talk about today is just what we can look for in graphs of polynomials in order to solve for solutions of polynomial equations. This is a relatively simple technique, but something that is a good opportunity to review and just look at. And then I want to look at how we can identify zeros of a polynomial and use those zeros to recreate the polynomial that it is. And then as a final step, I want to look at a number of examples where you can identify zeros as well as their multiplicities just by looking at the graph of a polynomial. So let's get started with skill number one, which is this idea of solving polynomial equations by graphing. And one of the things I want to point out, because it may seem relatively intuitive and obvious, but at the same time, it's one of those things that is worth mentioning every once in a while. And the idea that if you ever want to find the zeros or roots of a given polynomial function, you can do so by graphing. All right, and this is assuming that they are real solutions. And that would be a limitation in this given instance. But one of the things that I want to point out is that if you ever have an equation where you have it equal to something, a lot of times what we've done to this point is we've subtracted the negative 7x from both sides and then set it equal to 0. And that is a perfectly acceptable situation. But sometimes it just doesn't feel intuitive to do that. And if it doesn't feel intuitive to do that, I just want to mention that we can do the same thing that we did in chapter 3 of our textbook, is we took linear equations and we set them equal to each other. Well, the same thing applies to polynomial equations. So if you ever want to find the real zeros of a given polynomial function and you have parts of the polynomial on both sides, you can always set up each half equal to itself, because again, we're just finding the 1 point or 3 points in this given case where they will be equal to each other. And you may ask, how do I know if it's 3 points? Well, I have a cubic polynomial here, so that tells me that since it's a third power polynomial, that there has to be 3 potential zeros or roots, so to speak. And they won't be zeros, they'll just be real roots in this case because they won't cross the x-axis necessarily. But if we were to graph this in Desmos, what I would do is I would just simply set these two equations as y equals equations. And if we just substitute one into the other, we would get the original equation that we have here. But the reason I show you this is that sometimes this can be a really useful way to go and dissect your zeros and figure out where they are for a polynomial function without having to do as much rearranging, which might be really practical for real world problems, word problems and those type of things. Because all we would need to do in this case, if we wanted to find where the zeros of the polynomials are, assuming they're real, is that you would just simply identify the zeros where the two lines intersect. Okay? And these would be the solutions for this given equation. So if x would equal negative 3.5, then both y's will be the same, as you can see by the two functions or the two systems of equations intersecting. If x equals 0, both sides will also equal the same, and if x equals 1, they would all be the same. And this can be a really quick technique for finding all the solutions for a given equation that we may have, right? And there's nothing preventing you from moving the 7 over. I just wanted to take a minute to just tell you that this is something that you can do, and it can be really useful for finding real solutions. So just keep that in mind. If you have imaginary solutions, you won't see them, okay? So something to keep in mind. So let's talk about making a polynomial function using a graph. All right, so I have a situation here. I set the equation equal to 0, and then I went and I found all the zeros of the graph using Desmos. So I can see I have 4 zeros here. So my roots or my zeros are as follow. So we have zeros of C negative 3, negative 1, 1, and 3. And what I want to point out here is that whenever we're looking at this, we can actually make a polynomial function with this information really easily without even having the equation. And how we do that is we just simply look at the points, and if we know these are the zeros of a polynomial, well, you know that if you have a polynomial as such that you say x plus 3, okay, this is a binomial, and if you plug the 0 of negative 3 into this binomial, then it would equal 0, and anything times 0 would equal 0, and that's how we get this specific point on a graph. All right, so if you ever want to make a polynomial function using a graph, we can just literally build the polynomial function using all the zeros. Okay, so there's a 0 of negative 3, there is a 0 of negative 1. Okay, so the idea here is if we plugged negative 1 for x, it would equal 0, and that would give us this root or 0 on the polynomial function. We can keep going forward and just say x minus 1. So that would be a situation where we plug this root in, and then x minus 3, a situation where we plug this root in. Okay, so we can go and literally plug all these components in and find our polynomial function. So for example, what we could do is I could look at this. I could say, hey, this is the difference of squares. And the equation for the difference of squares is a squared minus b squared is equal to a plus b times a minus b. And I just want to point out that that's the scenario here, so we can kind of give ourselves a little bit of a shortcut here and say y is equal to x squared minus 1, because that would be x squared times 1 squared. And then we have x plus 3 and x minus 3. This is also another set of difference of squares. So we would have y is equal to x squared minus 1 times x squared minus 9. And the reason I point this out now is that if we FOIL this, we FOIL the x squareds first and get x to the 4th. And 9x squared minus 1x squared would be negative 10x squared. And then negative 1 times negative 9 would be plus 9. And what I want to show you here is that I just made this polynomial equation to represent this line, and I want to show you the equation I actually plugged into Desmos to actually get this. It is the exact same equation. So I do have to make the assumption that the highest order degree is 1, otherwise I would have to be given another point. But with this information, with even just having the roots that I can identify on the x-axis of the graph, I can figure out the equation of the polynomial relatively quickly. So with that said, I want to expand this even further. I want to go and I want to identify the zeros and multiplicities from a graph. And one thing that we noticed before is that it was a 4th power graph, right? And this is it looks like a quadratic. It's really symmetrical. It probably is a quadratic function. And normally I would just tell you what the power of the function is, but I'm just going to leave it blank at the moment here. But if I go and I look at this and I find my roots or my zeros, I see that my zeros for this given instance is just negative 3 and 1. So I just identified my zeros. But one of the things I want to point out is this idea of multiplicities. All right. And I'm looking at this graph, and based on its general shape, I think it is a quadratic function. And that means if it's a quadratic, it fits into the y equals ax squared plus bx plus c type format. And that means that the highest ordered power is 2. So that means that there should be 2 solutions, or a total of 2 multiplicities. So what that means in this given instance is that if I have negative 3 as a solution, it has a multiplicity of 1. And I can tell it has a multiplicity of 1 because it is a very linear behavior that passes through the point. And I'm going to show you a whole bunch of examples of this. But in a previous lesson, I talked about looking at a function and being able to tell whether it was linear, quadratic, or cubic, for example, based on the end behavior. And instead of looking at the end behavior of the entire polynomial, I want you to look at the end behavior of a specific root. So if we look at this root, we see that the end behavior is up and then down. Okay, and remember I said with polynomials that if you had opposite behavior, if you had up and down or down and up, that the power of that polynomial was odd. Now if you see that with roots, it means the multiplicity of that root is odd. Okay, so it means it's going to be like 1, 3, or 5, for example. And we see the same here. We see down and then up. So this root is also going to have a multiplicity that is odd. But the overall behavior of the polynomial is even. So the sum of the multiplicities should be even because we have up and up behavior at the end. So we see that -3 has this really linear behavior. We see that 1 has this really linear behavior. So just by simply looking at the graph, what I want to point out is we can identify that they have multiplicities of 1. Okay. Now, if that feels a little fuzzy, that's okay. I want to go over a whole bunch of other examples here so that I can kind of elaborate on what I'm talking about and what we're doing. But what I want to point out is that we have the sum of all the multiplicities is equal to 2, which tells me that the function is a quadratic. And in that given situation, we can see that we have a quadratic polynomial here. Okay. So without even doing anything else, I made all these graphs in Desmos and I'm just evaluating them. So let's look at another example. So here, what I want to point out is that when we're going through and we're trying to identify the power of a polynomial function, what we can do is that when we look at something like a linear function, there is no curves. And that is a first order or first degree polynomial. When we look at a parabola, there is one curve, which means it's a second order polynomial. And then if we look at a cubic polynomial, there are 1 and 2 curves, which makes it a third order polynomial. And what you'll always see is that the ratio of curves to the actual degree of the polynomial is you'll have 1 more power than you do curves. And so when we look at something, we can actually go and say, hey, I see this is relatively symmetrical. So I'm going to say that this is a curve. And this looks relatively symmetrical. So this is also a curve. And since I see 2 main curves, and that's all we see, then I'm going to assume that this is a third degree polynomial. So this is a cubic polynomial. And that is going to be the case for this specific model. So with that said, just by simple analysis of a graph, we can find some relatively useful information. Now, in a problem on your homework, I will tell you what type of polynomial you're dealing with, because this can sometimes be kind of hard, and then you know exactly how many multiplicities that there should be. But if this is a cubic polynomial, you should have 3 solutions potentially. Okay, so there'll be 3 roots or solutions, so to speak, to this polynomial. And really what that means is if there's 3 solutions, there is a sum of 3 multiplicities. But one of the things I'm going to point out here is that we only have 2 roots. Okay, so when we're looking at this, we see that we have a root of -3 and +1. but we have to identify the multiplicities of that root. And one of the things I want to point out here again is I see for this specific root, we have a down and then up behavior. And that tells me the multiplicity of this specific root has to be an odd multiplicity. We have like 1, 3, 5 as like a possibility. Okay. And at 1, we have a up and then up behavior. So where the vertex is, you know, we see it touches that 0, and then the end behavior along each point is up and up. So what that tells me is that the multiplicity of that root has to be 2, 4, and 6. Now, one thing I want to point out is that because it's a cubic polynomial, we know the sum of all the multiplicities need to add up to 3. Okay, so if we're looking at all the options, we can see pretty quickly that -3 has to have a multiplicity of 1, and the root of 1 has to have a multiplicity of 2. And if you want kind of a visual of what a multiplicity represents, it represents the number of times that number is a solution. Okay, so you understand the aspect, or we've at least talked about a number of times, this is zero product property. If we say A times B is equal to 0, if A is equal to 0 or B is equal to 0, then the product of those two numbers is 0. Okay, we take advantage of that with the quadratic equation and all these other types of scenarios. So if we look at this and we want to identify these multiplicities, you would just say, hey, if we want to make a function from this, we would just say x plus 3, okay, because if we plug -3 in here, this would be 0. That's a multiplicity of 1, so that's this to the first power. And if we say x minus 1, that's this root here. Since it's an up and up behavior, we know that this has to be a solution twice. Okay, so that means that this binomial is squared, so that means that the solution of 1 is a solution 2 times, and that's why we only see 2 roots, even though it's a cubic polynomial. Okay, so we can actually go and again crank out these functions simply by looking at the graphs. And there are obviously some limitations. Like I said, the a value or the leading coefficient would need to be 1 whenever we're dealing with this, and that's all I'm going to ask you to do. But I'm just trying to develop your skill and ability to look at these graphs and be able to go, hey, I can tell what the relative power of this, I can tell what my solutions are, and I can tell what my multiplicities are just by looking at these graphs. So let's look at another example to kind of continue on here. So here, again, I haven't told you what the power of this polynomial is yet, and I'm going to tell you on the homework, but one of the things before we even get there, I just want to point out is that there's a curve, there is a new curve, and then there is a third curve. Okay, so there are 3 curves, and since there's 3 curves, you always go one number higher than the number of curves you have. So that tells me that this is a 4th degree or quartic polynomial. So there should be 4 solutions. But one of the things I'm going to point out here is that, hey, there's 2 for this given situation. So these are your zeros. So if we have zeros of -1 and 1, zeros are roots, we want to identify the multiplicities. And again, you need to look at the end behavior. You need to see the up and then down for this root, and the down and then up for this one. So we can see that that the options are either 1 and 3 or 1 and 3. And the sum of these multiplicities need to equal 4 because this is a 4th degree polynomial. So now we have to look at and decide which ones has a multiplicity of 3 and which one has a multiplicity of 1. Well, if you remember back from the polynomial behavior video that we did, we talked about a linear function looking like this. This is what a linear or first power or first multiplicity root looks like. And if we talk about a cubic which is a third order, it tends to be a little smushed and then goes down. So there's those two curves that are there. And with a linear function, there are no curves. So what we can do is that I can actually look at this, and what I'm going to notice here is that, hey, there is a cubic looking behavior through this root. The root will always be in the middle of that behavior. So that tells me the -1 is the root with a multiplicity of 3. And the 1 here, this is a relatively straight line, there's not really any curve here, is the root with a multiplicity of 1. Okay, and if we were going to write this out as a function, you would just say x plus 1, which is the -1, 0, that would be cubed, and x minus 1 would just be the single power, and that's how you would write out this function, and you would identify those multiplicities. Okay, so if you see a trend, great. Otherwise, just keep looking at some of these examples here. I'm going to go through some more. Oh, and it's a quartic polynomial. All right, so, and I'll tell you what the strength of the polynomial is. So if we look at this one, I'll just tell you now that this is a nonic polynomial. This is a 9th degree polynomial, so there should be a total of 9 roots. And what I want to point out here is if we look at all of these individual roots, we see down, we see up, we see up, we see down, and we see down, and then up. And I created this example intentionally because I wanted to show the difference between these different power roots. So if we have 1, 2, and 4, and we want to find the multiplicity, we'll just go mul for short. What I want to point out is that all of these are up, down, or down, up behaviors. So that means that the multiplicities for all of these has to be odd. Because all the behaviors are varying in that way. Now, what I want to point out is that with this first root, we see this really linear behavior. There are no curves. So the first root here has a multiplicity of 1. Now, if we come back down over here, we're going to see 2 distinct curves. And what the curves do is as you get more curves, it smushes this polynomial flat. It gets flatter because there's more curves next to the root, and then you see this cubic shape that forms, okay, in this particular instance. So this root most likely has a multiplicity of 3. We know that this is a 9th degree polynomial, so the sum of all the multiplicities should equal 9. So now let's look at this last one, and I'm going to assume that this one has a multiplicity of 5. And there's a couple different reasons, right? I see a curve forming way back here, okay? And because of how flat this is, okay, I know it's a little subjective and we're kind of comparing here, but we see how flat this is. There kind of has to be another change or curve here, change in curve there, and then it curves back up. So that tells me that there are different curves or changes in slopes that are relatively significant in all those places. There's 4 curves, okay? And so the multiplicity or the power of that root is equal to 5, okay? So again, if you wanted to see what I originally created in Desmos to create this, which you could use Desmos and do this if you wanted to, would just be you have x minus 1 to the first power, x minus 2 to the third power, and x minus 4 to the fifth power. And that would be how I created this graph. And we can identify the roots, we can identify the multiplicities just by looking at the graphical behavior of these given functions. So the main thing that I want you to be able to do, and what I'm going to test you on specifically, is can you look at these roots and identify their multiplicities? So now let's look at this one. This is a dodecac polynomial, and what I'm going to show you here is that we have up and up again, and look, up and up again. So what I'm going to tell you about this specific polynomial is that all the multiplicities are even, because all of these roots have to have even powers representing them. Okay, so let's look at the roots, or zeros, in the multiplicities. And what I'm going to do is, I know it's a dodecac polynomial, and what that means is that this is a 12th degree polynomial. So if we're looking at this given instance, I want you to take notice that all three of these look a little different, and as the multiplicities get higher, you tend to see things being smushed or flattened as you go through. So I picked this example and created this example specifically so we could kind of look at it and say, all right, this specific polynomial here looks most symmetrical. It's not very smushed along the x-axis. We can tell it's coming down and barely touching. There's not really any more curves than the one that is represented right at the point. So the root that is equal to 2 has a multiplicity of 2. Okay, because we know since these are even multiplicities, we're talking about options like 2, 4, 6, and 8. Okay, and just know again that, you know, the sum of all the multiplicities that you have for any given function has to equal the power of the polynomial, assuming that all the roots are real and they're not imaginary. And I'm not going to throw situations at you where there is imaginary values and then ask you to find the multiplicities, because the whole point here is that I'm trying to get you to look at these and see if you can identify the behavior. Now, with this specific root, though, we see that there is, you know, kind of this curve, and then there's a couple curves over there. So there's some curvature here, and it flattens it out a little bit, not a lot, but a little bit. So I'm going to say that this root here has a multiplicity of 4. And now the last one I'm going to point out here, again, and I'm just trying to show you a specific example so you can see how they tend to differ a little bit. But this one, you'll see that there is a curve here, 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 and here. Okay, very subtle changes. But you can see that there are really 5 places where you see a adaptable change of slope here. And what that causes this root to do is, as it passes through the root, as it crosses the x-axis, it really flattens out that point. It becomes very much sloped with the x-axis, and you'll see that it really kind of meshes with it. And what I'm going to say is that this has a 6th multiplicity. So again, how I created this, just so you can kind of see it again, is you have x minus 1 squared, to the 4th power, x minus 2 to the 2nd power, and x minus 4 to the 6th power. Okay, and that's how I created it in Desmos. All right, one last example here, and I want to give you a little bit of a mixture. Okay, so let's practice and see if we can even identify what the power of this polynomial is. So here I see a curve. Okay, I see, you know, at least 2 curves here, maybe 2 more here. It's a little hard to tell. And then we have a and then we have at least 1, 2, 3 curves there. So what I'm going to mention here is that I see 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I'm wondering if this is a nonic polynomial. Oh, it's actually a decac polynomial. So that tells me there are 10 roots. Okay, so I missed a curve. Oh, there are 3, 4. Oh, okay, there are 9 curves. Sorry, I just didn't draw that one there. So this is a decic polynomial. Okay, so there are 4 curves there. And just what I'm trying to point out here is that we can actually see some of these right away. Okay, just by looking at the graph here. So one thing I want to point out is that since this is a decic polynomial, this is a 10th degree polynomial. And I am worried about these curves if I'm worried about the overall power of the polynomial. But what I'm going to do here is I see that this is up and down behavior at the root of 1. So if I'm looking at the root of 1, very linear behavior, no curves present right next to the root. So the multiplicity of that curve is 1. I'm looking at the root of 2. I again see down and then up behavior. That means the multiplicity is odd. And since it's a decic polynomial, I'm assuming something like 3, 5, or 7. Now, before I even started looking at it, I saw that there was 4 curves. Okay, so since there's 4 curves, you take the numbers one above that, and that tells me that you have to have a 5th power polynomial or a 5th power root in order to have 4 curves. So that tells me that this is a 5th, that the root of 2 has a multiplicity of 5. And then at 4, okay, if we have 1 and 5, that's 6. So that means that this root here has to have a multiplicity of 4. Okay, so we say 2, 4, 6 would be our possibilities. 4 would be the case. We see that 1 plus 5 plus 4, the sum of all the multiplicities is equal to 10, which matches the power of the 10th degree polynomial. Okay, so again, if I was going to write this out, assuming a leading coefficient of 1, you'd have x minus 1 to the 1st power, x minus 2 to the 5th power, and x minus 4 to the 4th power. And so when you're looking at this, just keep in mind that there is a lot that you can tell just by looking at a graph. You can identify the zeros present. You can identify the multiplicities of those zeros. You can tell whether it's a linear, quadratic, cubic, quartic, quintic polynomial or a higher, just by simply looking at and trying to find the curves that are present and where it crosses the x-axis. So keep that in mind when you're going through this video and that you're looking at these examples. I'll give you some simpler examples to practice and get used to. I'm just trying to introduce you to it. But with that in mind, I hope you have a better understanding of polynomial functions and their graphical behavior. And let's do math.